Okay, so welcome back to the Oxford Discrete Maths and Probability seminar. So as usual, everyone's muted. If you have questions, please ask them in the chat, and Christina and I will curate them. So it's a great pleasure to have Luke Postle, who's going to talk to us on further progress towards Hadwiger's conjecture.
All right, thank you. Thank you, Alex and Christina, for inviting me to this seminar to give the talk. Yeah, so today I'll be talking about Hadwiger's conjecture. So you probably all know about that, but we'll just go over the basics again. So really, Hadwiger's is about two fundamental concepts in graph theory. Coloring, which is the subject of probably thousands of papers. So a k-coloring of a graph G is an assignment of colors 1 to k to vertices of G, such that no two adjacent vertices receive the same color. We say G is k-colorable if G has a k-coloring. And we're interested, of course, in the minimizing this number, because you could just color each vertex different. And that's called the chromatic number of G, denoted chi G. It's the smallest case such that G has a k-color. So that's one way to think about it, is with colors, or alternatively, somehow it's partitioning the graph into independent sets. So it's also kind of a decomposition flavor as well. So that's coloring, which is widely studied. And then there's another concept that shows up in structural graph theory called minors. So we say that a graph G has an H minor if a graph isomorphic to H can be obtained from a subgraph of G by contracting edges. So we're allowed to delete edges and vertices, that's the subgraph, and then we're allowed to contract. So here I have a little picture, and I contracted the red edges and deleted that vertex, and I got a triangle. So you're maybe used to that. Maybe less used to is kind of the inverse of that, which is equivalent. It's called a model. So let H be a graph, and let's order the vertices of H, V1 up to V2. So a model of H in a graph G is a collection of vertex disjoint connected subgraphs, H1 up to HT, such that whenever you have an edge in H, Vi, Vj, you have the HI is adjacent to Hj. And by that I mean there is an edge with one end in HI and the other end in Hj. So if you look at that picture, say I wanted to find the triangle with V1, V2, V3, then on the graph on the left, you have H1, H2, and H3 as connected subgraphs, and indeed there's an edge with one end in each pair. And you can see that if you go back to this picture, really models are just kind of the inverses, the pullbacks, right? So if I could find my minor by contracting, then if I kind of undo all the things, I'll get back to those connected subgraphs. And so it's not hard to see that G is an H minor if and only if there exists a model of H in G. So that's kind of another way to think about minors. Same way that coloring had like decomposition or labeling aspects, minors can be viewed as both an operational definition, but also somehow it's something more structural, that it's finding lots of kind of connected pairs, pairwise adjacent connected subgraphs in a graph. And so these are two very fundamental concepts in graph theory. And it's kind of, here's the question, do coloring and minors have any relation? Now, if you've seen Hadwiger's conjecture, you say, of course. But I mean, I think you should stop and think about that and realize there's really no reason that these concepts really have to have any relation at all, right? Because, so coloring, you're decomposing into independent sets, and minors or models, you're finding kind of lots of disjoint connected pairwise adjacent subgraphs. And so why should, if I can't find those, I should be able to get a nice decomposition. This would be very nice as some kind of duality theorem, but we shouldn't somehow take it as a given that these are related at all. So I think that's kind of the amazing part about Hadwiger's conjecture, that we forget you're relating these two kind of fundamental ideas. And so what is Hadwiger's conjecture? So it was made by Hadwiger in 1943, and it says that for every t at least 1, every graph with no kt minor is t minus 1 colorable. And of course that'd be best possible. A kt minus 1 doesn't have a kt minor, but is t minus 1 colorable, you just color it all different. But so somehow it's saying though, yeah, if you can't find, again, that kind of this large model, then you can actually color well, and it kind of is in tight a way as possible. So what's known? So Hadwiger had shown in the paper introducing it that he proved it for every t at most 4. So, if no k1 minor, then you're empty. No k2 minor, you're an independent set. Those are easy. No k3 minor means that you're a forest, and those are indeed bipartite. 4 is where is not too hard. It takes maybe a couple pages. I should mention Dirac independently proved this as well for t at most 4. And then when you get to t being 5, well, that's hard. So Wagner actually, before Hadwiger's conjecture, and this is kind of what inspired it, in 1937 showed that the T=5 case is equivalent to the famous four-color theorem, which at the time was the four-color conjecture, which was eventually proved by Appel and Hawken in 1977. So why? Because basically it would imply the four-color conjecture, because planar graphs have no K5 and K3 minor, and so you would need that. But Wagner showed basically no K5 minor is kind of like planar graphs, but with maybe some additional things stuck on that aren't too hard to color. So won't get into that, but now we know from the four-color theorem that indeed the 5 case is true, but that's very hard. And then amazingly, Robertson, Seymour, and Thomas in 93 showed that the T=6 case is also equivalent to the four-color theorem and hence true. So if you don't know the four-color theorem, right, that takes computer programming, millions of cases to check, code to run, somewhat controversial, but now well settled. But also then Hadwiger's, you need the four-color theorem for all future cases, right? Because you could just take a planar graph and append an apex vertex adjacent to it all. And if you could 5-color that, it means you 4-color the planar graph. So really, the amazing part of the theorem is they said, okay, assume the four-color theorem, we can reduce it to that. And still, even assuming it, their proof is 100, 150 pages. And so it's a lot of work. And that's kind of basically where we're at. So it's open for T at least 7. 7 seems very hard. So there's some kind of partial results about what numbers you can get, or maybe if we exclude an additional minor, and I won't go through those. But if anyone could do 7, I think that could be considered a major breakthrough and be very hard. So we've kind of stopped looking at that and start looking more towards weakenings or general bounds and things like that. So what general bounds can I get? So let me not talk about special cases, but just what, if you want to exclude a KT minor, how good a decomposition could you get? So one thing would be nice is called linear Hadwiger's conjecture. This was kind of conjectured by various people, Reed and Seymour, Karbashi and Mohar, saying just, weakening. Let's not try to hit, exactly T-1, but, is there some C where every graph with no KT minor is CT color? So this would get rid of some of the hardness, right? Because for planar graphs, we can 5-color pretty easily, 6-color definitely pretty easily. So trying to say, let's not get the exact number, but just in the right order. But even this is widely open and seems very hard. But what else can we do? Well, there's a nice degeneracy argument. So graph G is called D-degenerate if every subgraph of G has a vertex of degree at most D. This is kind of essentially the same or up to constant as maximum average truth, you know that. And a greedy algorithm shows that if G is D-degenerate, then G is D plus 1 colorable. So this is how you show planar graphs are 6 colorable, they're 5 degenerate. So what can we get with that? So here is an old question then that arose. What is the degeneracy of graphs with no KT minor? Kind of what's their average degree? If I have large average degree, I should expect somehow a KT minor. And this was resolved by Kostochka and Thomason independently in the early 80s. They showed that every graph with no KT minor is T root log T degenerate, and hence T root log T colorable by this simple greedy algorithm. And so, this was kind of a nice culmination of earlier work by Motter, kind of showing that there was even some bound. So, this ties minors and coloring together because somehow minors, you get a large minor if you have large enough average degree. And so this was essentially kind of the best bound for the last roughly, almost 40 years now. So there have been some mild improvements. So Thomason figured out exactly the right constant there. So I should mention, this theorem is tight. So if you take a random graph on roughly T root log T vertices with, GNP with a half, you're going to find no KT minor, but you're going to have high average degree. So, but Thomason figured out exactly the right number, and then Wood kind of made an additive improvement. And with my student Tom Kelly, just last year, we had made a multiplicative improvement to whatever that number was, 0.998, and that was hard, coming from other things. But really, there'd been no movement at all in this T root log T bound until amazingly last year, there was a very nice result of Norin and Song showing that for every beta at least 0.354, every graph with no KT minor is OT log T to the beta colorable. So they really broke this degeneracy barrier, right? So that's kind of the amazing part. You have this degeneracy, and really, so these best bounds in Hadwiger's conjecture didn't use coloring at all, right? They just kind of used the degeneracy essentially. And so that seems very unsatisfying to the spirit of Hadwiger. Hadwigers, right? Is that somehow it should be about coloring in minors, not just coloring in minors and degeneracy. And so they did that. And then I came along and improved one part of their argument and showed that for every beta greater than a quarter, every graph with no kt minor is t log t to the beta colorable. So we ended up merging our efforts into one paper now. But really, yeah, somehow they had this really nice roadmap in a sense of how to attack Hadwigers. And I'm going to go through that in a bit. But so basically, you know, so we did finished off kind of one half of that roadmap and got to this nice t log t to the beta. So that was the recent progress from kind of last year into the beginning of this year. Okay, so I'm going to return to that, but I wanted to just mention a couple variants of Hadwigers. So I just wanted to survey. So Hadwigers has inspired a lot of work in minors and coloring, and it's ended up with a lot of variants. So let me just mention a couple of those, because we're actually going to need some of these. So firstly, here's one way to weaken Hadwiger's conjecture, is instead of looking for coloring, that would mean you could partition into many independent sets. That would mean you'd have to find a large independent set. So actually, Duché and Menil in 1982 kind of showed linear Hadwigers for just finding one independent set that's large. They showed that every graph with no kt minor has an independent set size, at least number of vertices. So I'm going to use V of g to note number of vertices over 2t minus 1. So kind of with the factor of 2 there. Right, so Hadwigers would imply this with v over t minus 1, but here we get, not a linear version of that. And I'll just mention Woodall showed a stronger result that kind of implied by the proof that actually there's a set of vertices on at least half the vertices that has a chromatic number most t minus 1. We'll use that later. But so you had this independent version, but then in another breakthrough, Reed and Seymour in 98 showed the fractional version of this, so strengthening it, showing that every graph G with no kt minor satisfies the fractional chromatic numbers at most 2t minus 1. And I won't get into what that is, but just kind of imagine that you're allowed to fractionally assign colors. And that's dual defining like weighted independent sets that are large. And they did that. So that was very nice. These things were known in these independent set and this kind of fractional coloring versions. There are other ways, though, so I just wanted to mention them if you haven't seen them before, to weaken Hadwiger's conjecture. So here was a couple nice stream of work in this recent decade. So one is called defective coloring. So a d-defective coloring of graph G is an improper coloring, so it won't be proper, but where each color class is maximum degree of most d. So instead of splitting into independent sets, you could kind of split into low degree graphs. And there's a nice theorem by Edwards, Kang, Kim, and Seymour from 2015 that shows if you have no k, there exists some d such that if you have no kt minor, then G has a d-defective coloring with actually the right number of colors, with t minus 1 colors, and that t minus 1 is best possible. So somehow, if you're allowed to kind of squint, if you're allowed the color classes to just kind of be defective with a degree, then you can basically prove Hadwigers. And the proof there is only maybe a page, so that's very nice. And the defect, as it turns out, is t log squared t, is what they showed. And I'll just mention that Van den Heuvel and Wood just in 2018 improved this to the best possible of t minus 2. So I thought those were very nice. So again, showing people are really thinking about this. Hadwigers seem hard, so let's weaken it. Let's show that it's in spirit true in other ways. And there's another one like that, which is clustered coloring. So it's kind of even stronger than a defective. So we see clustered coloring of graph G is improper coloring, where now instead of max degree, you do max component size. So you don't find a large monochromatic component. And there's a theorem that, again, there's a C such that if you have no kt minor, then G has a C defective coloring with some f of t colors. So I won't get into what the C's are, but what's the F? I didn't say here, because this is actually a stream of work from lots of different people. So Karbash and Mohar showed 31t over 2, would improve this to kind of 7t over 2, Edwards et al. To 4t minus 4, Liu and 3t minus 3, then Van den Heuvel and Wood I mentioned to 2t minus 2, and it's been announced by Dvorak and Norin that they can actually do t minus 1, but that's not been, I think, fully written yet, but is kind of long. So that would be best possible again. So again, people very interested in Hadwiger's, finding what we can prove. So these kind of weaker notions all end up holding there. Okay, so that's for weakenings. let me turn to generalizations. I know this is wrong because we haven't proved Hadwiger's, but people are still, inspired by Hadwiger's to ask, could stronger things be true? So one of them is nice. It's about odd minors. So we say a graph G contains H as an odd minor if a graph isomorphic to H can be obtained from a subgraph G prime of G by contracting a set of edges forming a cut in G prime. So that's a bit wordy. Kind of another way is the model, like you have each part be bipartite, and then you kind of need the edges across to be from the same color classes. So somehow it represents a parity condition, an oddness. And there was this odd Hadwiger's conjecture by Girard and Seymour from the early 90s that every graph with no odd KT minor is T minus 1 colorable. So somehow that, you can actually find the minor in a nice parity way if you can't color it, right? Because if it's like kind of more bipartite, then that should of course still color. And what's known about that? Well, Gielen, Girard, Reed, Seymour, and Veda in 2008 showed to get T root log T color. So that doesn't follow directly from degeneracy, because bipartite graphs have no odd K3 minor, right? But can have arbitrarily high kind of average degree. But they were able to kind of crank this and add in other arguments to the Kostochka and Thomason down and show that it also holds for odd minors. And then Norin and Song in a follow-up work have actually extended that quarter proof to now work for odd minors as well. So T log T to the beta for every beta greater than a quarter. So this nice quarter result now also holds for odd minors, which is nice. And then there's a different generalization I wanted to get at, which is also list coloring. So you may have heard of this. So introduced in the 70s, it's been around now, many papers. So a graph G is K-list colorable if for every assignment of lists L of B. So at each vertex I give it its own private or its own list of colors, could overlap or not. And I want to find a coloring phi of G. So again, adjacent vertex is not the same color, where the color comes from the list. So this is of course kind of a generalization of coloring where all the lists would be the same. And it turns out then, could you ask, the Hadwiger's for list coloring? No KT minor, your T minus 1 list colorable. And Margit Voigt, she showed in 93 that actually there's a planar graph that's not even for list colorable. So the 4-color theorem doesn't hold for list coloring, and hence list Hadwiger's is false, right? But in another nice result, Barat, Jouret, and Wood in 2011 extended that construction to show that graphs with no K3T plus 2 minor are not 4T list colorable. So it's not even that it's off by 1 or 2, it's actually off by at least some multiplicative amount that you need, that at least 4/3 as a ratio. But it could still be true that linear Hadwiger's is possible. And because the Kostochka and Thomason bound, I should mention, degeneracy also implies list colorability. This greedy argument, you can just greedily color from lists. So that was kind of, again, the state until this recent progress. And with Sergey, him and I were able to extend the quarter result also to work for list coloring as well. And unfortunately, the list and the odd don't generalize simultaneously, because it turns out, again, no odd K3 minor bipartite graphs or have no odd K3 minor that can have arbitrary list chromatic number. So you can't get both at the same time. So they're two different directions to go in, but we managed to take the quarter in both directions, which I thought was very nice. So those were some weakenings we reviewed, some strengthenings, and kind of the spate of recent progress on that. But now I wanted to get to our main results, which is not recent progress, but further progress. That's the name, further there. And so what's our main result for today? I'll try to sketch some of the ideas of the proof. But what is the main result is that for every beta greater than 0, every graph with no KT minor is OT log T beta colorable. So we can get this quarter all the way down to anything bigger than 0 that we want. So we can kind of go sub-logarithmic in that area, that extra term. So I think that's very nice. So this I did in June, and then I'll get to it, but there's some, then it becomes a question, what's the actual function, right? I mean, is it 2 to the square root log T or what? Well, I made some iterative improvements to that, and finally, I won't go through this, details not in this talk. The best version is from September now. So every graph with no KT minor is OT log T to the 6th colorable. So we can get to log realm. Unfortunately, there's a 6 there, and you'll see for reasons kind of log naturally appears in the proof, and it'd be nice to improve, that 6 to 5 or all the way down to 1, and then it's going to get harder. But this seems kind of satisfying to me. We're out of the log realm and into the log realm. So that was the state from September. And then, so I gave this talk a bit ago before, and I said, okay, that's kind of the state. Then I went back and thought about it more and realized with 6 or 7 additional ideas, some new ones, I could extend this to list coloring as well. So every graph with no KT minor is T log T6 list colorable. And at the same time, using some of the ideas from list coloring and some more additional ideas, I was able to extend the odd version as well. So that's T log T to the 6 colorable for the odd one. So yeah, I posted that now as some separate paper because it really complicates, you have to do 10 or 12 more pages to really get these lists and odd things to work. So I'm not going to cover that in this talk because it would kind of distract from the main narrative. And I won't go through exactly why the 6 comes up. You'll see where it comes up, but I won't go through those details as well. So really focusing just on that first result. How do we break this, log T to the quarter barrier? How do we get sub-logarithmic? Because some really nice ideas come up there. Okay, so if there aren't any questions, I don't know if there were any questions from the chat or anything. We're good. Okay, so then I have to actually really to explain the breakthrough to the 0 to I have to explain the quarter first. So I'll proof overview from the kind of joint paper with Sergey and Zizio. So how do you even break the square root barrier? That's kind of the first part. So here it's not too bad once you put all the right ideas together. So here's one. So here's a nice idea. We can color small graphs decently well. What do we mean by small? Very small, but like importantly the random ones. The ones that were holding up the degeneracy arguments where it's tight, those random graphs on T root log T, you can color them with like T log T colors or anything that's kind of T poly log T. And why? It's just a corollary of the Duché and Menier result from earlier. So how do you do this? There's a large independent set on at least 1 over 2 T colors, remove it. There's another large one, remove it. Keep doing this, and it turns out you'll end up with, if you had like T root log T, you'd end up with T log T colors. Or if you work it out, you get this formula. You get kind of T times log of number of vertices over T, say plus 2. So if you have a T poly, T log to the 10T there, you get T log T on order. So that's the first thing. We can color small graphs decently well. What else? Well, can we find a small graph? So this is actually a nice kind of theorem. So for sake, let the density of a graph G denoted D of G be edges over vertices, which is really just half the average degree. And here's a nice question. When does a graph of density little d have a minor of density big D? Right? So think about it like this. I'm trying to color. I know I have high minimum degree. So I have like density roughly T. If I could only get to density T root log T, then I'd have a complete minor by the Kostochka and Thomason math. So can I do that? Well, obviously not all the time. What's the obstruction is small graphs. So obviously, if my graph has number of vertices less than big D squared over little d, there's just not enough edges that no matter what contractions I do, I won't find this kind of high density minor. So that's one obstruction. But you might say, okay, but we know how to color small graphs for Hadwigers. Is that the only one? Well, you can obviously take disjoint unions of such graphs. So you can just have kind of every component being small. And that's an obstruction. But kind of if you don't have kind of dense small graphs, can you do this? And the answer is, in spirit, yes. So here's a nice theorem. So for every S, there exists a G of S, such that if you have a graph and say it's non-empty, and we let S kind of be the ratio of big D and little d, where little d is the density of the graph, then you can get two outcomes. Either you find your higher density minor, that's outcome 1, or you can find a subgraph where the number of vertices is that big D squared over little d times G of S, and the density is roughly the original density, D of G, over g of s. Except this is, of course, meaningless because I haven't told you what g of s is. But think of it as kind of this error term to the outcome we want, that the obstruction is a small dense graph. Okay, so now I tell you what g of s is. Well, this was the key to the Norin and Song improvement, is that they showed that g of s, there is actually a g of s, and there was one that wasn't too bad. So they did s to the alpha for any alpha, say 0.7. And then in that work from the fall, I improved this to actually, you can get it sub any root. So it's s to the alpha for any alpha that's greater than 0. And so this was nice. And then at the time, more specifically, it was like 2 to the log s to the 2/3, but it was something. And then the work from this year that gets you the 6th is actually just improving this function to 1 plus log s to the 6th. Because you're going to apply this when when this ratio is like square root log t, and then instead of something 2 to the root log t or something, you're going to get log t there, and then that's where the log to the t6 come from. So currently the bottleneck for Hadwiger's is right here. It's just improving this function, and I don't know what the answer is there. It could be, certainly log s seems like an option. Maybe it could even be some constant. So we don't know what maybe the lower bound is. Not that there won't be other bottlenecks, but this is the current bottleneck. Okay, so that's a density increment theorem. What can you do with it? Well, as I suggested, then you can find small graphs, right? So here, let f of t be, 3.2 squared g of 3.2 log t. Basically, that'd be on the order of log t to the 6th. A corollary of this is that if you had a graph and your density was at least, say, k times f of t, this kind of error term that's log t to the 6th, and g contains no kt minor, then I can get you a small graph. So vertices at most tft log t, which is t poly log t, so one of those small graphs, and the density at least 2k. So I can find, if I don't have a kt minor, I can find a small subgraph that has basically the same density as the original graph up to this f of t from that error. Why do I write 2k there? Well, it turns out it's more useful to not instead look at a dense graph, but a connected graph. And there's a nice theorem of Motter from 72 that if you have density at least 2k, then you contain a k-connected subgraph. And so I could just rewrite this to, you actually have a small k-connected subgraph at the cost of f of t. Okay, so we're going to make use of that. And corollary, you repeat this, however many times you want. And not only can you find one of these, you can find our vertex disjoint of them, as long as your chromatic number is at least kf of t plus something like t log f of t and 6t log r. So it turns out those numbers will work for us, but basically you can kind of keep extracting small graphs. And the point is, we know small graphs are colorable, so if you don't take too many of them, that colors. So what remains doesn't color, so at high degree, and then you kind of repeat the argument. So this allows us to kind of extract as many small graphs as you need. Small, dense, they're highly connected. And that's great for building minors. Okay, how do you build minors? Well, this is where I need two other ideas from the literature. So one is linked. So if you haven't seen this before, this one's nice. So graph G is called k-linked. If for any set of vertices S1, SK, T1, TK, you can get internally vertex disjoint paths PI from SI to TI. So here's a picture. So if you've heard of Menger's with connectivity, right? Menger's tells you when can you get K paths from a set S to T. Here, though, it's ordered. I really want S1 to go to T1, S2 to go to T2, etc. Right? So K connected will get you unordered, but I want it to be ordered. But there's a nice result of Vlogt and Thomason from 96 that says you can do this with just a constant, though. So if you're omega K connected, so something like 22K connected, then you're K-linked, depending on how you define these terms. And the best result on that is Thomas and Wolin from the 2000s, which is something more like 10K linked. 10K connected gets you K-linked. So here it depends how you define it, because do you assume these vertices are disjoint? So the way I wrote it, no, it doesn't make a difference except for the constant, essentially. Okay, so that's one idea we need. And then the second idea, which actually I decided to name because it's this nice idea of Sergey and Zizhia's, but it turns out it's going to be important to our proof, so let's give it a name. So I thought there's linked, let's call it woven. So a graph G is AB woven if for every 3 sets of vertices R, S, and T. And here's a picture. I can find this kind of ST linkage, this set of paths, but I can get them disjoint from a complete model. So a complete minor, remember, but in this model form. So I can find a Ka model in G that's called rooted at R. So what I mean by rooted, each one of the R vertices appears in exactly one of the sets. So each one is going to contract when you contract down onto each of the R's. So I can really find a complete minor on R, and that's disjoint from this nice linkage. So there'll be AB woven. A for the complete minor and B for the linkage. And you could do this, the claim is you want to do both of these. And here's this nice theorem that appeared in Sergei Nzigia's original archive preprint. It didn't have the language at the time, but it says this. If a graph G is omega A root log A plus B connected, then G is AB woven. So if you set A to 0, this is the Thomason theorem. And if you set B to 0, you'll notice that this is kind of like the Kostochka Thomason theorem, right? But now actually I can not only find that, I can find a rooted minor. And this allows you to do both at the same time. So as long as you're at least A root log A plus B on that order, you can both find a rooted minor and you can find a linkage. And this basically then lets us do the quarter proof. Once you have all these ideas, you can do small graphs. You know about wovenness now as a generalization of linked and the density increment theorem. You put it together and you can get the quarter. So I'll just run through that. So what do we do to build the minor? Well, you let y be log t to the quarter and x to be t over y. And I won't go into it, but by work of Kobayashi, you can assume the graph is xy squared ft connected if you have high enough chromatic number. The chromatic number is on the top there. It's log t to the quarter times f of t. Then by our density increment corollary, I can extract many vertex disjoint highly connected subgraphs. So xy squared. So xy squared is t log t to the quarter there. And I'm going to draw a picture of that. So here's how it goes. So I'm going to have an H0, which will be viewed as the hub where I'm going to build the minor. And then I'm going to kind of make a grid. So here I'll maybe kind of upper triangular grid or matrix of these other graphs. So H11, H12. So I have all these small, highly connected graphs. And now how do you build a minor? Well, inside H0, let me build up sets to connect the minor. And then in each Hij, I'm going to choose kind of a set of vertices. And so the idea is I'm going to build my KT minor by kind of building, I'm going to split up the T into these sets of size X. There's going to be Y of them. And I'm going to build every pair having a minor, and I'm going to link it all up. So here's how that goes. Since I'm linked, then by the Thomason theorem, I'm linked, I can get lots of paths. So I can link every S1 up to its row and every S2 to its row, but also its column. So I can link everything to the rows and columns. And then I just build minors inside each of these little squares to connect every pair. And then inside H0, my hub, I do the connecting to link up these various pairs of complete minors. So how does that work? So here I've linked everything. I've kind of pre-processed how I want to do the minor. And then for every square, I weave a model rooted at the Tij, right? So I had some Tij where I was going to build the minor. I can do this with that kind of weaving theorem. I know each of these Hij is woven in the right way. Except there's slight technicality. Okay, at the beginning I had the right number of paths, but you might complain that the paths dodge in and out of Hij, so I can't obviously preserve all of those paths. But I don't have to preserve all of them. I just have to preserve getting from the first to the last point. I just have to preserve the overall linkage. So if you look at my picture, you can see that if it dips in and out, actually just link that first vertex to the last one inside and forget about the outside. And if you do this, so if you kind of get that idea in your head, you can actually preserve an overall linkage while building a complete minor in any way you want from this woven idea. And so you just weave the minor, you apply it iteratively, preserving the linkage, weaving the complete minors, and then back in H0, it's also highly linked you can just link up each of the s's and you then build to a minor. So that's where you have the t log t to the quarter. So kind of the quarter comes because it's exactly between half and 0. So if you go through that analysis with the x and y, it turns out, you need this square root business inside each of those squares. You need kind of square root log, and it turns out log to the quarter is exactly what will do that for you. So this is pretty good, like this quarter. The issue is it's somehow not good enough. So where's the further progress? So that's what I'll try to talk about in my remaining time. What idea do you need to break it? And so somehow the issue is, how do you build a minor? And so what we did there was, okay, we find lots of little subgraphs. We know we're linked. We link up to them and have them do it. But it's kind of like trying to build it all at once, right? It's building it globally kind of all at once. And I'd like to suggest there's better ways to build a minor. And so this is the idea that I'm kind of thinking of this year is, so here's 2 better ways to build a minor. And they would kind of naturally occur to you. One is recursively. So imagine this, like instead of building the minor, build 3 kt2/3 minors and link them, right? So divide into thirds and pair them and kind of like recursively build. So instead of building kind of that's what we did, except we dropped way down to some small level. I'm just kind of suggesting let's build that and then maybe have them recurse as well and kind of build a little bit smarter that way, recursively. The other way is sequentially. So instead of building all at once, let me successively build up a kt minor by adding like square root log t new vertices sometimes. So let me build it, and then I'm just going to build a little bit more, and I'm going to build a little bit more. So, of course, these just seem like, okay, pie in the sky ideas. Okay, yes, those are nice. How is that going to be helpful? Well, actually, this is the key. So we're going to use these 2 ideas together to either one way or the other find the minor. So point of order, though, in each case, whether you're doing kind of many recursion levels or many sequential steps, you kind of need many large, highly connected subgraphs. So you're going to need highly connected subgraphs, but you actually need larger ones. Does that make sense, right? Because like if you're recursing, then I need to know I have many levels to go, or from sequentially, I need to know there's many places to go. So that's the issue in the first proof, is those nice connected subgraphs were small. If I could only kind of know that they were actually kind of small but decently large, that they had a chance to have things inside them, then I might have hope. And this is the struggle. What resource do we have for forcing large graphs? So this is where I got stuck for a while, and for good reason, because the answer that we need was only done in the spring of this year. And the answer will be the chromatic number. So that's the resource we have, is don't forget coloring. We have chromatic number. So connectivity doesn't really do this for you, but the chromatic number can, right? Because small graphs color. So if you have a high chromatic number, the small graphs lemma tells you then actually you'd have to be somewhat large. But can you use chromatic number to also guarantee high connectivity? And that's a nice result this year of João and Arianen, because Sergey had posed a question actually at the Banff conference where we were talking about this, whether this was true. So I won't go through the history here, but some function was proof for this, but here's this really nice result. So for every positive integer k, if G is a graph with chi being at least 7k, then G contains a k-connected subgraph H with chi of H at least chi of G minus 6k. So it turns out, so it was kind of known that like you could do this where you could guarantee, like if I had k cubed, I could get down to k, or k squared, I could, but they're really saying, actually, I can get you k connectivity as a subgraph and only lose something linear in k. So, that's quite strong. So like basically for just a small cost, I can get you the connectivity. So this will mean basically, and that's what we'll repeatedly apply, is we'll find high chromatic subgraphs. I'll apply this theorem, give up a little bit, get high connected, and I'll actually I'm using the chromatic number as a resource because that means it's kind of large, that there's more, steps I can do, because I'm just going to throw away a little bit of chromatic number each time I do these steps, and so I'll be able to do many steps if you do them in the right way. Okay, so also if you haven't read their paper, it's very nice. Like it's really from the book, The Proof. It's maybe 3 or 4 pages. So it's amazing though that 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 somebody hadn't actually thought of this proof before. It's like it's just so classical. So yeah, so that's just a plug for that. But so we're going to use that. And now we need our key concept. So how do you end up in recursive versus sequential? So here's this idea of separability in a chromatic form. So we say a graph G is s-chromatic separable if there exist two vertex disjoint subgraphs H1, H2 of G with chi at most, at least chi of G minus S, and then you're s-chromatic inseparable otherwise. So we just kind of a notion, you know, I have a high chromatic graph, does it kind of contain two still pretty high chromatic subgraphs that are disjoint. So call it s-chromatic separable then, and it's inseparable otherwise. Now, obviously, not every graph is separable. Cliques are not, they're very inseparable, but there are ones that are. And so it's you know, can we use this? But here, you should really think of S as very small in terms of chi of G. So kind of, if you think through it, obviously, if you have a chi of G, you can find two subgraphs with roughly like chi of G over 2 chromatic number. That's too much to pay. Really, it's kind of like I want to find, you know, very like two ones that have almost all of the chromatic number to go together. And so this leads to two cases. So you might think separable versus inseparable. Actually, I'll say it's always separable versus inseparable. Kind of as I go in, can I always separate, or am I inseparable? And this leads to two lemmas. So in the always separable case, it turns out chi is at least s log t, and every subgraph, say always means like with high, so at least chi of h is at least half the chromatic number. If you're always that amount of s separable, I can show you contain a kt minor. And similarly, there's an inseparable case where say s is at least t log t, and your s chromatic inseparable, and your chi is at least like t log t to the sixth, then you also contain a kt minor. So hopefully that makes sense as an idea. So I'll go through this if I have time. So in the inseparable case, we'll build a minor sequentially, and in the always separable case, we'll build it recursively. And if you put these two together, that proves the main theorem, right? And so you could look at that, but you know, you just apply it. Either it's always separable, done. Otherwise, I find an increment inseparable subgraph, and then the other lemma tells you you're done. Okay. So now in my time remaining, I'll draw you some nice pictures. You know, get all of the proof, and maybe we'll skip some steps, but of how to do this. So again, this I think it should be the really nice takeaway. Besides, like, you know, the woven was nice. The Stirano-Rhiannon theorem is really nice. But I think this idea of separability is very nice. And I was kind of actually inspired by the Alon Seymour Thomas proof, if you know it, for separators and minor closed. You know, if you're excluding a minor, that to build like the recursive, to build the sequential idea. And so somehow this, you know, it's a very natural dichotomy, like separators versus expanders, right? Always separable versus inseparable. So here's how the always separable case goes. So this is where woven comes back around. I'll actually show you, not a kt minor, I'll show you that you're, say, A0 woven, assuming you're originally connected, which you could by the Girard-Moran theorem at not much cost. How do I do that? Well, okay, so I'm separable. So inside G, there are two high chromatic subgraphs. Let me call them H1 prime and H0 prime. Well, here's a trick, right? I'm going to actually say, well, H0 prime is also separable because it's always separable. So then it has an H2 prime and an H3 prime, and you only lose another factor of S. Why am I doing this? Because it turns out it's better, instead of having two, to have three, right? For this recursive idea. You want 3 pairs. And so now inside of all of those, I'll apply the Girard-Moran theorem to clean up the conductivity. So at a factor of 6k inside each, I can get a k-connected high subgraph. And so we end up with this kind of picture, where I have my big graph, and I have 3 high chromatic, highly connected subgraphs. How do I build the minor? It's the obvious recursive idea that occurs to you that I've kind of already explained. So again, we're doing this in woven. So we want to build a rooted minor on the R's. I can assume the subgraphs don't use the R's. It's not costly. And then what I do is, you know, I pair it into thirds. So we have the first third R1, the second third R2, the third R3. We want R1 and R2 to use H1, R1 and R3 to use H2, R2 and R3 to use H3. So we find sets of vertices inside them, just pick them, and then link, right? So I can do this. I can assume I'm, you know, appropriately A-linked. And then Okay, I've done that. Now I'm going to recurse. Right? So if you assume your two-way link, you get these paths. And now I just recursively weave a model rooted at ti inside each hi while preserving this overall linkage. So, if we were at the point where we could apply Norin and so on, good, but here this would do it kind of recursively. And this is why you need this woven idea to do the recursion. And so you kind of just do it inductively. So what happens? Well, the size of the minor I'm building goes down by 2/3 each time. So you kind of have an A1, which is 2/3 t, and A2 will be 2/3 squared t, right? It's decreasing. But the issue is I have to also, now my B grows, those linkages I have to preserve grow. So the first time I get 2A0, if you go back to this picture, you'll see they're down 2/3, but I actually have kind of 2A0 number of paths there. And then the next time I'm going to get 2A1 and then 2A2, etc. But importantly, I only have to preserve the linkage of things above me, only parent linkages in this kind of recursive tree. And they're getting smaller. So you're going to get 2 times the sum of the AJs, but each time they're going down by 2/3, the geometric series is out to 6t, amazingly. And if after log t steps, the A's have gone down to something like t over log t, and you can just apply the Norin-Song-Woven theorem, and we're done. And so it all works out very nicely. And how much chromatic number did we use? Since it costs log t steps, you can work out the numbers, but it'll work out. So it'll be like, S or K times log t, which will be enough. So that's like, somehow I had this idea way back when that if we could have these recursive, it would all work very nicely. I was stumbling on how to get the large ones, but this Norin and this chromatic number does it for us if we can separate. But now how do you do the inseparable case? Well, I'll just run through it quickly. The plan is you're going to build a minor, and you're going to build it in stages. So it'll be root log t stages. So this should be reminiscent of the quarter plan a bit, where each time we're going to have a set of x's t over y new parts, right? So I'm going to build it sequentially. And here's the key definition that we're going to need is, I call it tangent. So we'll say a model of H in a graph G is tangent to a subgraph G prime if every part has exactly one vertex in that subgraph. So you should kind of think like, I want to build it sequentially, so I have some subgraph G prime to work in. I want to make sure my current minor doesn't use too much of that subgraph, but has at least a toe in, it has its toes dipped into the subgraph, so it's tangent to it. So if we can kind of preserve this, it'll work. So here's our goal. So each step, we're going to extend our model to a slightly larger model, so from ix to I plus 1x. Again, preserving all adjacencies, making the new ones. We're going to ensure that when you remove the model, the chromatic number is large enough. And this will allow us, by Norin, to find a high chromatic number, high connected subgraph. And then we're going to ensure that we can make our model tangent to that subgraph. So it's like we kind of have a bank of high chromatic, high connected place to keep trying to build our model. We got to make sure we can do this, but also get to that future, get to it, but don't use it up too much. So step 1 is easy. It's just the old plan. So, to build one step, since your H is tangent, so let's say here are the toes, the U1 up to the UIX. By our density increment corollary, there exists. So here I don't need the full grid. I only need one kind of row or column, however you think of it. So I'll take a hub H0 and I'll have a column. And I'll just do the same plan. I'll link my old models, the U's, into the H0 as well. I'll link that up in pairs to the column, just as I did before. And we can do this with not even need linked. Just Menger's theorem will let you do it. And then we can kind of link and weave as needed to do the steps. So you link inside the hub H0, you weave individually inside each little square of the grid. So somehow that's not bad. And it doesn't, you're only doing one column, so it doesn't cost you that quarter, is the idea. It only costs you a linear number. So that is easy. The hard part, well, let's go through. So can you have large chromatic number left over? Well, the nice part is everything is small. right? I mean, the U's are small, all the H's are small. So they'll have small chromatic number, T log T by the small graphs lemma. You might complain, what about those paths that from Menger's theorem? Do they have large chromatic number? Well, there's not too many of them, and if you're not, silly and you make them induced, right? If you take shortest paths, then your chromatic number is at most like 60. It's at most like 2 for each or something. And so that will, there's T here, there's 2T there, 3T, each only 2. So that'll be fine. So actually you're fine. You only lose T log T chromatic number when you build this next stage of the minor. So that wasn't the issue. I got stuck on step 3. So this, here, I'll just run through, what some ideas. Do you, I know that there's high chromatic stuff. I make it connected. But how do I make sure how to get my minor from like the hub to that future? How do you get from the present to the future, right? So option 1 was, do you use Menger's to find paths from the future GI+1 to the hub? And the answer is no, because they obviously could intersect these nice paths that I was using to build. They might block you. My option 2 I came up with was you start the whole thing over. Now that I know where the future is, this GI+1, I'll just construct paths. Well, I'll construct paths from the hub to GI+1 while also doing those paths to the squares. And that actually also doesn't work, because if you start over, it turns out things that can go wrong. You may intersect your GI+1. You may end up kind of using the future and destroying it and losing its chromatic number. So all that is bad. So you know where the future is, but you can't find the paths and you can't start over. So here's the cool idea: redundancy. So one day I just woke up and it occurred to me, and then everything else just worked. And this is what makes the whole proof finally work, is you just ensure redundancy. So how do you do this? Well, in that first picture, instead of taking paths to the hub, I double all the paths. I make 2. Each vertex wants to get to the hub. I make 2 paths to the hub. So there's 2 ways for every vertex to get to the hub. Then, also using Menger's, I make double the number of the paths I need from the future to the hub. So double from the past to the present, double from the future to the present. And a simple exercise of Menger's theorem says that if you have this double redundancy, you can actually find single copies from the past to the present and from the future to the present. And then it just works. They kind of meet in the middle. And it's it's an easy exercise, but I don't think I've seen, I'd be interested if anyone knows. I haven't seen this anywhere. Like, it just works. It's amazing. So ensure redundancy. Okay, and then I have to say one last thing, and then I'll finish up. So there's one last problem I have to say. I lied about step 2. Is the chromatic number really large enough? Because I said we lose only T log T at each step. That's fine for the first step. It's fine for the first few steps. But I lied, because there are square root of log T steps, right? So you'd actually lose T root log T chromatic number. That's too much. And the solution to that is to rebuild the minor at each step. You can kind of do the next step and not lose too much. But now every time I do that, let me go back and rebuild it to be a little bit smarter, a little bit better. It's a bit wasteful. How do you do that? Well, what does the minor need from each HI? You only need really you need to connect the tangent vertex with all the adjacencies, just the little complete minors. And there are kind of few of them. And so there's actually a nice simple lemma to that if you actually had a connected graph and you have a set of terminals that you want to preserve, you can find an induced connected subgraph, which with a set only 3 times larger, that preserves the terminals, and the chromatic number outside of it is at most 2. So it's kind of saying, at the cost of tripling the small stuff, I can preserve the adjacencies, but I can make it so that all the paths kind of all work together. It's just kind of, I won't go through this lemma, it's easy, just inductively do it. But it turns out you can therefore apply this to each of the part of the model, and all the terminals will be small. So there's kind of small stuff, and then the rest only is chromatic number 2. And so I'll just kind of rebuild it at each stage. And so by the Girard-Norin theorem, then there'd have to be some large high chromatic, high connected subgraph. But let me just then finish on this part though, so here's the last trick. So I rebuild it. I don't lose too much chromatic number, but but you should think, I had this nice future all planned up, right? But it was too costly. So I pulled back, I rebuilt it, but that means actually I get a new future with slightly better chromatic number. But I knew I was tangent to the old future, but am I tangent to the new future? And so this is the question. There's two cases. If the old future and new future overlap in at least k vertices, they're both k connected, I can just union them, I can merge them into one big future, and then I'm tangent to that new future, the big one. In the other case, where they're not, like the old one I had planned up, which is pretty good, but not quite, and the new one, which is slightly better, if they're kind of that, just delete their intersection, and what have you found? You found your separability. You found two subgraphs, old and new future, with high chromatic number. So this is the amazing part. Up in this whole inseparable proof, I didn't use the inseparability until right now to finish it. I know I can keep going to the future. It's always the same future. And so we do that. And so in summary, we've proved this every beta greater than 0. A key was divided into these two cases. With the better density increment theorem, I could talk about, we get every graph has the t log t to the 6th colorable. And here's some future directions where, could we improve the density increment theorem, avoid dividing into cases, color small graphs better, etc. But I think that's where I'll end. And thank you.
Great, thank you, Luke, for a fantastic talk. So if people have questions, I think everyone should be unmuted, or at least able to unmute themselves. But please, maybe if you signal either in the chat or raise your hand so that we can loop you in. Actually, maybe first let me ask just a question or two. So you had this sort of dichotomy between always separable and inseparable. Mm-hmm. Now, because things are happening at slightly different scales. Is there really a dichotomy, or is that sort of, in fact, you could have dropped and then maybe run backs and forwards between the two cases?
Yeah, so I've been thinking about this. So I think I got it to work out, but I have to check one thing. I think the dichotomy is more like you have the inseparable case as your base, and in the separable one, if you found an inseparable subgraph, just use the inseparable as a kind of do the general with the inseparable as a calling, as a function call. The only thing is you need to make sure that the inseparable can also get woven. Right now I set it up to be KT minor, and so there's some slight. I think we can get rid of that, but there'd be some slight technicality to that. But I don't think inseparable needs to really call separable. Maybe there's a debate because the only issue is. If it fractures, I don't know. Okay, we managed to get to one of the subgraphs. I don't know how useful that is, because we also want to get to the other. So then just starting over and saying, let me build to the both at the time. So I think that's somehow it's a useful idea, but I don't know how needed. And maybe there's a proof that just kind of avoids this entirely. So that's I think what I mean by the last question. It'd be nice to not do this, but somehow it's a very attractive idea, right?
Yeah, that's very nice. The other kind of little technical question I had was about this path doubling thing. I didn't quite follow what the trick was for getting them separated.
Like how do you actually do this?
I just wasn't quite clear on the pictures, so.
Yeah, so imagine you have three sets, A, B, and C, right? Mm-hmm. A has, but every vertex has two paths to B from A, and every vertex from C has like two paths.
Okay.
Then it turns out, if you just check Mengers, I claim that there's an AC set of paths, because otherwise that there'd be a small cut. And if there's a small cut, well, it has to be cutting off parts of A and C, and one of them has to be at least half of that. And then the double paths kind of guarantee that there's no, you can't actually do this small cut thing. So and you can generalize this, doesn't have to be double, you could have K different things in each, having a redundancy of K. But like somehow.
So they can't, my intuition hasn't quite caught up, but so they can't cross in some sort of grid-like way and interfere with each other. Yeah,
like they could, but somehow the idea is you could then read. I mean, the magic is in Mengers, like you're just applying Mengers. But somehow, yes, if they did, it'd be they actually somehow get there. So of course you don't try to find the paths, you just try to argue there's no path in Hadwiger.
Sure.
But yeah, somehow I couldn't believe that this actually works, but I'm very hopeful that there's not a mistake there. This seems just true. So, but yeah, I don't know what the intuition is, other than it sounds like it's a nice thing that should be true.
Do we have any other questions? Let me ask one more actually. So you've got this sort of beautiful ideas getting you down to this log t to the 6.
Mm-hmm.
So is there any hope of going beyond log? Sort of natural question, but
yeah. So the 3 current bottlenecks. So the big bottleneck is this log t to the 6 coming from that density increment there. As I said, though, I mean, there are good reasons where log comes up in that proof. I don't have time today to go through that, but there's no fundamental reason, if you came up with an entirely different style of proof, why it couldn't be constant. So that becomes a central question, but inherently is hopeful, right? Here, though, there's 2 other places where log shows up. So one is in this kind of recursion level. So if we could kind of stop dividing into cases or kind of luck out, maybe we could get rid of that. The other place it shows up is in the small graphs. And so that was why I asked at the end, could we, can we color small graphs better? So it'd be nice to actually prove that, like this t, log squared t vertices graphs, if you could show that they're t colorable, that's one of the other remaining bottlenecks to doing like linear Hadwigers. So right now it's these 3: the density increment, the small graphs, and maybe somehow the cases, kind of getting rid of that recursion a bit. But that's where I'm hopeful. Yeah, somehow it feels like this is the right proof if we're going to do linear Hadwigers. Now that's a lot to say. Maybe there's just some different proof, but it would be nice if that was the case, right? And so that's where I meant that. So Norin and Song, I mean, they didn't have the separability thing, but their idea about the small graphs that kind of first showed up kind of gives you this idea that there is a roadmap to this kind of proof, I think. And then with a separable and separable, it ends up working out. And it's still like hopeful that if we could just get better, this would be the roadmap to linear Hadwigers. Obviously not to Hadwigers, because there's lots of times you pay constants, but maybe to linear Hadwigers.
okay, thank you very much. Are there any other questions? Okay, in that case, let me invite everyone to unmute themselves, and let's have a big round of applause to